Can you hear me? Okay, great. I'm Yono. Welcome to Computer Vision, not just for breakfast anymore. If you're here hoping for lots of great breakfast content in this talk, I'm going to have to disappoint you. This title is what's known as a placeholder title that I was totally going to change before my talk. Nailed it. All right, so who am I? Along with Alice Zhao, I am the co-creator of Gus on the Go, this friendly little owl guy. He introduces small children to new languages and teaches them some words and does simple stories with the goal of making them good global citizens. I'm also a freelance software developer. I've done many things, but I specialize in computer vision and iOS. I'm a tutorial writer for raywendelich.com. If you've read my tutorials and liked them, thank you very much. If you've read them and didn't like them, come talk to me. I'd like to know what I can do better. If you haven't read them, you have homework, but wait till after the conference. Uh-oh. I'm going to pretend it's going to come up again. Kind of. It's struggling. Hold on a second. I'm sorry. Try again. All right. And I once drove Bruce, don't call me Ash Campbell, to the airport while I was studying at CMU. So, will any of this be on the test? No. Why did I talk about all this? Well, John told me I had to speak for 40 minutes, and I could only come up with about 38 and a half minutes worth of content, so here we are. Okay. When I was a kid, I used to watch a sketch comedy show called Kids in the Hall. They came from Canada, and they were a little bit on the wacky side in terms of content. If you think of the spectrum being going from Saturday Night Live to Monty Python, they were absolutely closer to the Monty Python side. Their humor was very wacky and influenced me as a child. In particular, one sketch that I really enjoyed was known as the crushing your head guy or the head crusher. And this guy, using the power of perspective, would, oh my goodness, that's... All right, let's see what we can do here. All right. He would pretend to crush people's heads between his fingers from afar. Try a different port. Okay. So, but what does this have to do with computer vision right now? I'm glad you asked. Introducing Crushing Your Head, the app. Kids really love this one. I know I'm mixing up references here, but this is my first talk, so bear with me. In this talk, we're going to be creating the basics of a game or an app where the user will be able to crush people's heads and earn high scores, all using computer vision. So what kind of computer vision are we going to use in this app? Well, the user's not going to be able to touch the screen. They're going to be using their hands. So we might need a hand pose detector. We're going to be crushing heads, so maybe a face detector would be good. We might want to compare feature vectors. If you don't know what that means, it's okay. We're going to go over it. Object tracking could be useful. And as a bonus, we might even train our own custom image classifier. But before we get started with that, let's talk about Apple's Vision Framework. This is the framework we're going to use to create the basics of this app, because it allows us to do a lot of things. The Vision Framework allows us to create or do a lot of common computer vision tasks very easily using very little code. It's also optimized to run on iPhones and iPads, and I think possibly the M1 Max. So since we're all developers probably coding for iPhones, iPads, this is probably useful. And by optimized, I mean a lot of vision tasks run on the neural engine. which leaves your CPU and GPU free to do business logic and rendering the UI, which keeps your app snappy. It's also updated yearly with new features and new APIs. So how do you use the Vision framework? The Vision framework follows a pipeline, a very common pattern among all of its APIs. And you start with a request. This request, along with the input image, gets fed to a handler. The handler will process the request and return the result as a property in the original request object. Requests can be lots of different things, anything from detecting human hands. I like how they say human hands. Detecting face rectangles, detecting text. There are two different handlers that we can use. There's an image request handler, which processes one image at a time, and then there's a sequence request handler, which also processes one image at a time. But the difference is the sequence handler can store information about previously processed frames to help it detect objects in the future. The results that you get back are usually analogously named to the requests, just with observation at the end. So, I mentioned earlier that I write for raywindow.com. I do mostly vision tutorials there. For instance, I did a tutorial on photo stacking, where we would take a bunch of frames using video function and align them using a vision API, average the pixels together, and in doing so, any object that would move through the frame relatively quickly would disappear from the final image because it's not contributing that much information to each individual pixel. This is a technique that's useful if you want to take an image of an empty street, but there's always cars on there, or say you're at the Eiffel Tower and there are too many people there, and you want to get a nice clean shot of the whole place. This is one way to do it. I have a tutorial on saliency analysis, which tries to figure out what is the most attractive part of the image. By attractive, I mean what's going to attract the user's attention or the viewer's attention. And you can use this then to create interesting filters for photos. Additionally, I've done a tutorial on face landmark detection, which I teach you how to shoot lasers out of your eyes. Okay, back to crushing your head. Let's start with the hand pose detector. So the hand pose in the app offers a unique game mechanic. So you're not going to be touching the screen. The user is going to interact purely with the camera on the iPhone or iPad if they're holding a very big iPad. We're going to simplify this by just looking at the tip of the index finger and the tip of the thumb. We don't care about the rest of the points in the hand. And we're going to say if the two tips are vertically close together, then the user is pinching or crushing. A hand pose request can detect up to 21 points in the hand. It'll detect 3 points on each hand, plus the tips and the wrist. The lines are just interpolated between these points. Oh, and don't forget, human hands. I'm actually very interested in seeing what would happen if I take this to the zoo and try to use the app on gorillas or orangutans or something. Maybe that's my next project. Okay, we'll take a look at some code, how to do this. So we first have to create the request. In this case, vn detect human hand pose request. Human hand pose. We're going to configure this request. And in this case, we only care about one hand, basically the hand right in front of the camera. So by setting the maximum count to 1, we're going to simplify our code later on. And it's going to allow the iPhone to process more efficiently too. What happens if more than one hand appears in the frame? It's going to take the largest one, which is going to be the user's hand that's pinching. We set up a request handler. And the image request handler, we're going to pass in a CV pixel buffer. The image request handler can actually take lots of different things, including CG images, CI images. It can take URLs. But CV pixel buffers are what we get out of our A/B capture session. So this makes it fairly easy. We perform the request. We first wrap the request in an array so that, because each image handler can actually handle multiple requests simultaneously. After we perform the request, our results are attached to that original request object. We check to make sure that we are getting back human hand pose observations. If you're not, then you have a major bug in your code, or Apple has a very major bug in their framework. We also only look at the first result because we only care about one hand. And then we create a pinch from that result. Okay, let's look at a face detector. Face detection in the app. The goal of, there's going to be a lot of photos of me on this, mainly because I don't want to take pictures of other people and without their permission, so yeah, I'm not that vain, I promise. The goal of the app is to crush heads. And as software developers, we like to make things easier for ourselves. If we can take a shortcut, we're going to take it. So since Apple doesn't have a head detection API, but they have a face one, faces are fairly good proxies for your heads. If you find a face, you can be reasonably sure that there's a head there. Now granted, this won't allow you to crush people's heads who are not facing you, but that's a trade-off I think I'm willing to make right now. And if we detect a pinch is within the bounding box of the head, we know that the head has been crushed. Perfect. So, face rectangle requests. What kinds of faces can we detect? We can detect normal faces, well, as normal as my face is. We can detect profile faces, obscured faces, which is super relevant in today's modern world, small faces, and multiple faces. I'm not going to lie, I might have faked that last image. Let's take a look at this request. It's going to look fairly familiar to some of you. We're going to create the request first. This time we're going to configure it using a region of interest. By region of interest, what we do is we narrow down what part of the image we send to the API for processing. In this case, you can imagine that the image is mapped to the unit square. So your bottom left-hand corner is 0, 0, and your top right-hand corner is 1, 1. And in this case, what we're doing is we're taking 20% off of both sides. So we're going from 20% to 80% of the image. We're going from halfway up the image to 30% from there up. And this is because normally you're going to find faces in that region when you're crushing them. You're not going to find faces below that. We're going to create our image request handler just like we did last time. We're going to process or perform the request. And we're going to look at the results. This time we're going to get face observations. The results we're going to map to our head objects. And what you'll notice here is that each result has a unique identifier and a bounding box. The unique identifier is going to be important later. So there's one problem. Do you know what it is? Yeah. Players can game the system. You can crush a head multiple times. You can rack up a high score in no time, and that is not what we want. So how are we going to solve this problem? Well, let's take a look at comparing feature vectors, see if that can do something for us. But first, let's talk about feature vectors. Apple calls them feature prints. Other literature will call them feature embeddings. But a feature vector is nothing more than a bunch of numbers that describe the characteristics or the features of an image. So what can we do with them? How can we compare them? Or sorry, how do we generate them first? To generate a feature vector, you're going to take a model. It can be a deep neural network, but it doesn't have to be. However, nowadays it's almost always a deep neural network, so that's what we're going to use. You're going to pass in your image, and the model is going to spit out a vector of numbers. The number of dimensions of this vector is dependent on the architecture of the model. These vectors can be anywhere from hundreds of numbers, or hundreds of dimensions, to thousands of dimensions. So how do we compare them, though? Let's start with a simple two-dimensional vector example. Let's say we're comparing vectors A, B, and C. How do we know which ones are more similar and which ones are less similar? Well, looking at this, we can say that A and C kind of point in the same direction, so they're probably more similar. But A and B are pointing in very different directions, so they're going to be less similar. Well, that's just nothing more than their angles, right? And we can calculate their angles using a dot product. We're actually also going to take a cosine of the angle because the cosine will give you a number between -1 and 1. 1 being they're pointing exactly in the right direction, 0 being they're orthogonal, and -1 meaning they're pointing in the exact opposite directions. This dot product trick for comparing and calculating the angles works even for thousands of dimensions, which is what I said, which, as I said, is nothing more than a feature vector. So we can take these feature vectors and use a dot product to compare them. We're going to pass our images through the model, we're going to get our feature vectors out, and the ones that are more similar are going to come out with smaller angles. So in my case, the two right images are more similar than the two left images, at least I hope so. What can you do with this? Well, I worked for a Norwegian startup called View, and their goal is to make the app for movie nerds. Basically, they wanted to be able to include any and all kinds of information about a movie, but specifically for each timestamp in the movie. So not only which actors are acting at that particular scene, but where the scene was filmed, what songs are playing, what products are in the shot, and trivia and stuff like this. The thing is, they have this database of information, and the user could look it up by going to a movie, finding the timestamp that they're currently watching, and then seeing all that information there. But they wanted something a little bit more magical, not so manual. So what we did is we came up with this feature where we would scan a TV. So we would use actually Vision's API request to detect rectangles to detect where the TV is. We'd do a perspective correction on it, crop it out, pass it through our model, and get feature vectors out. We had already run movies through the same model to calculate feature vectors for every single timestamp, and then we could compare those feature vectors that the user was seeing with the feature vectors in our database. And in this case, it correctly identified that I was watching Spider-Man Into the Spider-Verse at the 1 hour, 11 minute, and 6 second mark. It was really cool. So let's see how to do this in code. And remember, Apple calls them feature prints, so it's not going to be a feature vector here. So we're going to generate a image feature print request. We're going to configure the request. In this case, what we're going to do is we're going to do a center crop of the image. When you pass, the models used have a fixed input size, so they're going to have to rescale your images. And much like rescaling for a UI image or an image in a Swift UI, it has to know, wait, what can I do to this? Can I center crop it? Should I scale fill it? Should I scale fit it? In this case, we're going to do center crop. We're going to create our request handler just like last time. Are you noticing a pattern here? I hope so. We're going to perform the request. And then we're going to get the results. There's only going to be one result for each image anyway. And Apple, unfortunately, doesn't give us an array of floats or an array of doubles. Instead, they give us data, just pure raw bytes. So they tell you, they at least tell you what the precision is, whether it's floating point or double. So you're going to have to convert those to an array of numbers yourself. Okay, so now we know how to calculate feature vectors. Know what you're thinking. This is perfect. We can calculate where a person is pinching. If they've pinched over a head, we save off those feature vectors into a database or into memory. And the next time they pinch, we compare those feature vectors against everything we've already crushed before. And if they're crushing something they've already crushed, no score change. It's not in the app though. And it's not in the app because of 3 reasons. It requires determining a similarity threshold, which is a lot of trial and error. So what's a match? Is 90% similarity good enough? Is 75 okay? Do you need 95% similarity to determine whether someone has already been crushed? It also depends on whether Apple's proprietary model can discriminate between faces. Maybe their model can tell the difference between dog breeds, but it's face blind. Without testing that, we don't know. Also a lot of work. And as I mentioned earlier, we like to take shortcuts. So there's a simpler solution, which takes us to object tracking. Object tracking. I mentioned before that each result has a unique identifier. If we use this unique identifier to track objects through the frames using a Vision API. This way, we can prevent MHCs or multiple head crushings. We only have to check to see if the UUIDs match. All right. So, can you guess what we're going to do now? This is going to be a little bit different than the other ones, but still very, very similar. So this time we're going to create an array of requests, because you need one request per object that you're tracking. Since we can track multiple heads simultaneously, we will need to be able to handle multiple requests. We're going to have a local property where we store a dictionary of tracked heads. We have UUIDs as the key, and then the detected object observation as the value. Every time we go through here, we can create a VN track object request based on those observations, and we attach them to our request array. If the request array is empty after this, we know that we had no heads that were being tracked, so we have to start new by using our detect face rectangles request. Also, if we're starting over, we want to reset our sequence handler, because here we're using the sequence handler instead of the image handler. It'll be important, and it'll be important for being able to track heads through frames. We perform the request just like always, even though it's a sequence handler instead of an image handler, it looks very similar. And then we go through each request, we go through each request results, and we update our tracked heads dictionary. But what if crushing heads is too gruesome? What if you're worried that your app is going to be only available for 17 plus, and you're going to miss out on all that money from kids? Or what if you want to do a fun seasonal aspect to your app? How about smashing pumpkins? This brings us to our custom classifier. We're going to create a pumpkin classifier using create.ml. I'm going to show you the steps how to do it at a very high level. First, you need to collect lots of images of pumpkins and lots of images of not pumpkins. I want to say be mindful of image licenses, okay? Just like if you're going to use an image in your app, you have to have the proper license to be able to use it. If you're just building a prototype to make sure that it would work, then it's okay. But once you start building something that's going to go into production, you definitely want to make sure that you have collected data properly. It's only ethical. After you've ethically collected your images, you're going to structure them in folders. You have a test folder and a train folder. The test folder is actually optional, but helpful. The train folder is very important. Underneath the train folder, you're going to create a folder for each of your classes. In this case, a pumpkin and a not a pumpkin. You're going to organize your images based on their class into these folders. You'll then create an image classification project in create.ml. And you're going to have to add the training data to create.ml. And so all you can do is drag that folder over to that training data box. It automatically detects that you have two classes. It says here 46 images. You're going to need probably more than that, but this was just a sample. What happens if you only have one class? Like, why do you need that not a pumpkin class? Why can't you just detect pumpkins? Well, if you had just one class, you're going to get an error from create.ml. And the reason is the model's going to need to know what is not a pumpkin in order to better learn what a pumpkin is. Otherwise, it has no idea how to differentiate between pumpkins and not pumpkins. After you've hit the train button and your model trains for a bit, you can evaluate it using that test folder, or you can spot check the model. For instance, here, we passed in a pumpkin, a jack-o'-lantern image, and it correctly identified it 100% confidence that it's a pumpkin. I put in an image of myself from a long time ago, and it correctly identified me as not a pumpkin, despite me wearing an orange hat. You can export the core ML model. You can either save it, open it directly in Xcode, or use a share sheet. All right, let's talk about image classifiers. And this is going to tie back to the feature vectors that we learned about already. The image classifier is going to use that same model that created the feature vector. You're going to pass in the input images. It's going to generate feature vectors for all of those images. It's then going to use those feature vectors to train a classifier. Now, you might be thinking, you've heard that machine learning models are large. They can be anywhere from a couple of megabytes, which is not that large, to hundreds of megabytes. Or if you're Google or Facebook or OpenAI, hundreds of gigabytes. And those definitely won't fit on your phone. Well, let's take a look at the model pieces. So just the model and the classifier. The model is Apple's proprietary model. This is actually shipped with iOS. So everybody's phone, iPad, automatically has this model already installed. All you're doing is training this classifier. This classifier is only 17 kilobytes. That's pretty impressive. And so when you add your core ML model to your Xcode project, it's only going to copy the classifier part. And it knows it needs to use the internal model to actually do the entire pipeline. All right, so how do we use this in the app? We're going to create a core ML request, and based on the model. We're going to specify a region of interest. So a classifier only can tell you whether or not an image is a pumpkin or not. It can't tell you where in the image a pumpkin is. So because we don't know where the pumpkin is, if it's a pumpkin image, we have to do a little bit of a trick here. So what we're going to do is we're going to give it a potential rectangle, a CG rect, based on where the person's fingers are. That way, it's only going to show it a little bit of the image. If it detects that that's a pumpkin, then we know that the person's going to smash a pumpkin. If it's not a pumpkin, then it's not. So we're going to do the image request handler, just like always. We're going to perform the requests. We're going to look at the results. This time we're looking at VN classification observations. And we're only looking at the first result because there's only going to be one result for that. We check to see if it's a pumpkin, and optionally we can check to see if the model was very confident that it was a pumpkin. So maybe we want to say it's not really a pumpkin if the model only thinks it's 60% chance that it's a pumpkin. That's optional, like I said. And based on that, we can create our pumpkin object. All right. This is pretty much all the major pieces for this app. We've gone through hand pose detector. We've gone through a face detector. We've talked about comparing feature vectors. We've talked about object tracking and how that helps us prevent multiple head crushings. And we've even trained a pumpkin classifier so we can have a nice Halloween version of our app. I think the kids would be proud. But it's a little bit awkward to hold up your phone and your hand and then crush people's faces. It's not super easy. It'd be so much better if we had some sort of hands-free device, some sort of glasses maybe. I've looked deep into iOS. I couldn't find evidence of AR glasses. I'm not that good, but I think I found proof that they're not going to be doing AR glasses. They're going to be doing an AR monocle. All right. The code for this app is available on GitHub. If you have any questions, feel free to take a look at it there and let me know. I've been Yono. Thank you very much. I went a little bit fast. Sorry. Yes?
I got a couple questions about finding images. You mentioned, make sure that you check the rights to your created images. What is the best way to ethically or legally or whatever find images, all mass, or at least your favorite way of doing it? And what kind of non-pumpkin images will you train on?
Okay, I'm going to repeat the question. I'm going to take the first one first. All right, so you asked, how does one best ethically collect data to train machine learning models? That is a very good question, and that's not always easy to find out. There are lots of public data sets out there. And often a public data set will have a license attached to it. So sometimes you'll be able to know whether you can even use pieces of a data set that's already out there or not. Sometimes you won't be able to. Various websites will also list licenses for individual images. That can also be time consuming, but data collection in general is time consuming. You can also capture data yourself. So you can go around your neighborhood around Halloween and start taking pictures of all the pumpkins on people's doorsteps. Just make sure. I don't know if you might need permission from the people. I don't know. Yeah, maybe. And then the second question was, what kind of not a pumpkin pictures did I include? That's a very good question. That's going to depend on what your goals are. In my case, I didn't do a lot of testing with this, so this was a very kind of fly by the seat of my pants moment. What I did was I took images from neighborhood streets. My theory was, besides Starbucks during pumpkin spice latte season, most pumpkins you're going to be seeing are going to be in front of people's doorways and stuff like that. So I took images from neighborhood streets that didn't include pumpkins, in the thinking that if you're going to be using this app Halloween time, that's most likely the data it's going to come into contact with. So essentially, you want your training data to be as close to what you expect the usage data to be like. Anybody else? Are there any questions on that? Over there?
So, thanks for the great talk. My first question is, can you get a hyperparameters in the output model? And the second question is, if you train your own output from your own method, like your test book, can you flip it out of output?
Okay, so the first question was, can you mess with the hyperparameters for Apple's model? No. So it's pre-trained. it's on device. You can't even. It's also proprietary. So if you were to change parameters on it, my guess is it wouldn't work anyway. When you're training your own model, there are options for training that you can actually play with. I just use the defaults for this because it's just easy. It's fairly reasonable, but there are a little bit that you can play with CreateML. What was the second question again?
You train your own model, like before, so I can switch it out and I take the app to train my model.
Yeah, so you can actually convert PyTorch and TensorFlow models to CoreML, and then you can just easily swap it out. That's the demo that I did with Vue. We actually used our own CoreML model as opposed to Apple's model to generate feature vectors, because we wanted to be able to do something that was trained on data more like that we were going to see. Are there any questions online? I can't see. All right. Well, thank you very much.